All right, here we go. We'll give this a try. I don't know, my brain's not working. But we'll try it. So just a little bit more, push forward a little bit more with the second derivative test. There's a couple examples I like to look at that seem pretty simple, and they are. Uh, but there's something happens in these two examples that is poses a little bit of a dilemma. Okay, let's take a look. So what about something like this? We know what this function looks like, x cubed, right? But how do we get that from the table? What's the derivative?
3x.
And the second derivative?
6x.
Okay. So now we've got our second derivative row, right, on our tables.
Oh, yeah.
The domain of this function is what?
Yeah, everything except 0.
How come we can't have 0?
Oh. Oh, no,
Yeah,
right?
that is-
No, then everything.
Everything, yeah, all reals. Okay, critical numbers. Where's the first derivative? Nowhere undefined, right? Where's it 0?
0.
Yeah, it's 0, right? So we only have one first derivative critical number where the function is 0. The fact that it has a 0 derivative tells us what?
It has a horizontal tangent.
Horizontal tangent. Okay, so then we could go to the second derivative test to determine what's going on there, right? Okay. So what's the value of the second derivative at 0?
0.
Aha. So the second derivative is indeterminate, right? It doesn't tell us the answer. It doesn't give us a sign.
It's a transition, or what's it called?
It's a point of
Point of inflection.
Well,
Well,
I know. I was so close. I was gonna get there in like 5 minutes.
Yeah, in 5 minutes. Okay, so that's you're correct. That's what it's going to be. But how would we know? Because at this point we don't know. At this point it could be either one, right? And this is really important. Just because the second derivative equals 0 does not necessarily mean that it's a point of inflection.
Oh.
So because the second derivative test fails, what do you think we do?
We have to pick points.
We go back to what test?
The concavity test.
I mean, we could. That's the table. Like we really could work in any row here. And I used to teach this as always working as far down the table as you could, because typically, especially when you're dealing with derivatives of polynomials, the derivatives get simpler. But I'm going to be in sync with what the AP test says on this one, because it doesn't make that much difference. The AP, and I get why this is probably, for a first-year calculus student, maybe this simplifies things. I don't think it does, but their rule is if the second derivative test fails, go back to the first derivative test, which never fails. It just takes a little bit more work because you have to pick test points there, whereas for the second derivative test, the beauty of the second derivative test is you don't need test points, right? All you need is a sign of the derivative at your 0 first derivative, and you got it, right? Remember from the video lecture yesterday, what did we say about this? Like if I'm in a table, and what if we get a first derivative critical number just arbitrarily like at let's say like at 4, so it's not 0. Okay, well you know that means horizontal tangent, right? Okay, if the sign of the second derivative there is positive, well, add those two things up. 0 first derivative plus positive second derivative means what? Yeah, that's bowl shaped up, right? So then that's a minimum. Okay, and there's this is kind of a dorky little mnemonic device here, but when you're applying the second derivative test, A positive second derivative means a happy function, so it's smiling.
Oh.
And a negative second derivative is a sad function, so it's frowning, right?
What?
Okay.
That
So
makes
cute.
it way easier.
Okay, so in this case, neither one of them, it's indeterminate. We don't get a sign of the second derivative, so we revert back to the first derivative, and we'll pick test points. We'll pick points like at -1 and +1, and if I go to the sign of the first derivative, notice that they are both positive. Okay, so that means it is not a minimum nor a maximum, right? So what is it? Well, it's an inflection point. Okay. The reason I tend to like using the second derivative line better, which again, I mean, this is the way that the College Board, AP people want you to do it. That's fine. Here's why I personally prefer going further down the table. Because you get the same information. Like if I were to check the second derivative, pick these test points, at -1, I get negative. At +1, I get positive, which tells you that if the concavity is changing from negative to positive, then this is an inflection point, right? If it hadn't done that, if it had stayed negative the whole time, then we would have known that this is a maximum because it was concave down the entire time, right? See what I'm saying? So personally, I like to go further down the table and just work there. Okay. Okay. Anyway, so now we know this is an inflection point because of that, right? And really, we didn't even have to have that information. If it's not an extremum, it has to be one of those things. If I get zeros in both, so if it's not an extremum, it's an inflection point. Okay, but filling in the concavity part just answered that for us. Okay, let's compare that to, and of course we know what this looks like, right? This is just, it is an inflection point, x cubed graph, right? What about the symmetry? That would have been nice too. What's the symmetry on this one? Odd or even? Yeah, it's odd. So we get this rotational symmetry about the origin. So again, that's a good clue for us, right? If I rotate this thing 180 degrees, it lines up. Okay, how about same thing with x to the fourth? Well, we know what x to the fourth looks like. It's just a flattened out parabola, right? Okay, so we know it's got even symmetry, and we know what it looks like. It kind of looks like that, right? With just a little square or base on it. But again, let's just show that on our table. So f prime, what's that, 12 x cubed, f double prime, 36x squared. Okay, same domain, all reals, same critical number, 0, right? 0 is the only critical number we get from our first derivative where it's 0. But again, the second derivative test fails. We get 0. Yes?
How is it 12 next to the
Did I mess that up? Oh, I did. It's 4. Gosh. Yeah, I'm blaming that on the flu. You're right. I don't know what was going through my brain there, but you're right. It's 4x cubed and 12x squared. Much better. Okay, so we'll revert back to the first derivative test again. So we'll pick test points. -1, +1. At -1, the first derivative is negative, right? At +1, the first derivative is positive. So we know that this is what? Zero first derivative is horizontal tangent. If the first derivative is transitioning from negative to positive, what is this? Yeah, it's got to be a minimum, doesn't it? Right? Okay. Like that. And we got it. Okay, good? All right. So same kind of thing. I remember why I picked this. Oh, I know why it is. Okay, yeah, this is a good one. All right, so we need to arm ourselves for our table. What do we need to do? In order to get critical numbers, we need derivatives, yeah. And let's add something to this. Let's do more, let's kind of start to transition into curve sketching, which is what the next section is after second derivative test. After this, it's just pulling everything we've done back together into using tables to sketch more complicated functions. So while we're at this, let's kind of try to look for more than just minima and maxima. Let's look for inflection points too. Okay, and inflection points. All right, so first derivative is what?
X minus 4x minus 16x 16.
Okay, so we've got to, while we're at it, let's go ahead and find critical numbers. Any place where that first derivative is undefined. No, it's polynomial, right? Polynomials are nowhere undefined. Their domain is all real numbers, always. Okay, to find out where it's zero, though, we've got to solve the equation where our first derivative is equal to zero, right? And so, yeah, so this is good review, right? Let's review this.
I know that.
Okay, so this is a four-term polynomial, right? So let's just remind ourselves, how do we solve four-term polynomial equations?
Grouping.
Grouping, yeah. But we want to do a test. We don't want to waste time with grouping. We want to do a test to see if grouping is going to work. And we know if it's going to work. To see if grouping is going to work, we just want to see if the ratio of the coefficients in the first two terms is the same as the ratio of the coefficients in the second two terms, right? That make sense? So in other words, 1 over negative 4, is that equal to negative 16 over 64?
Yes.
It is, isn't it? Yeah, okay. Okay, the other thing that has to happen for grouping to work is that the exponents need to be consistent. So I need to be dropping by the same power in the first group and the second group. Well, I'm dropping by 1 and I'm dropping by 1. So we know then by those two tests, we can see that grouping is guaranteed to work, right? So we can factor by grouping. Okay, so how did we factor by grouping then? Okay, good. We're into the first group. We're going to factor out an x squared, leaving behind. Okay, and then in the second group, we know we're going to get the same binomial. What goes out front?
Negative 16.
Negative 16. There you go. And all that is equal to 0, right? So then we end up with, when we factor the left side, it factors into x minus 4 times x squared minus 16. So what are my zeros then?
3, 4,
And
negative.
negative, right? Okay. So we get, those are my first derivative critical numbers. Okay?
Okay.
Second derivative. So there's first derivative. What's my second derivative?
3x squared minus 8x minus 16.
Okay? Again, nowhere undefined, but when what? Okay, when 3x squared minus 8x minus 16 equals 0. What's the quickest way to factor
Slip
that?
and slide.
I do group B. I would do group B.
Yeah, I'd factor this by, I'd factor it, I wouldn't use, I mean, you can always use quadratic formula,
Or 3x.
right? But does grouping work?
Yeah.
It does.
4.
To group it, we want to find magic numbers whose product is the outside product, right? So negative 48, and whose sum is negative 8. Well, what are those numbers?
Negative 12 and 4.
Negative 12 and 4. Yeah. Right. Does that make sense? And so that's how we're going to split the middle term, and we'll factor by grouping. Okay. I really do think that's probably faster than quadratic formula. You get all those big square roots and stuff. I mean, it works. It's fine. But then look, this is going to split up pretty easily. 3x squared minus 12x plus 4x minus 16. And if I find magic numbers, it's going to group. It's going to group. Right? We did this.
I've never seen this before.
This is how I factor. I
I
don't do slip and slide.
always do slip and slide.
Slip and
I
slide
do
is
slip and
stupid.
slide too,
I
and
do
then I just.
And if slip and slide doesn't work, then I do quadratic formula, but I don't like quadratic.
Okay, this is the same with you guys. I remember I taught you guys where I showed you slip and slide, but I told you I kind of emphasized this.
I think Mrs.
Yeah.
Jones taught us slip and slide. And we were all like,
Slip and slide is bad.
Could be.
No.
I really dislike slip and slide because
It's a
it's
cheat. It's a hack.
it is a cheat. It is a hack. It's a cheat. It's not.
okay.
I think all the cheats and hacks I can
Probably
get.
calculators
It's
smarter
hack,
than
but
ours.
we're not all
Ours do.
robots here.
It's-
Oh my gosh.
It's not algebraically rigorous. It's each step doesn't follow from the previous. Like when I teach it, I remember I have you guys. You have to do it as side work and come back to the problem because the equal signs are not true. You can't, like when you're solving a problem, you want to be able to take each side of the equation and you want to be able to equate it to the step prior to that, right? You don't do that with slip and slide. Slip and slide is kind of a hack. But with slip and slide, the thing is with slip and slide, you're doing the same stuff, right? With slip and slide, you still have to find the magic numbers, which is the hard part. Once you find the magic numbers, it's easy. Right now, once you find those same magic numbers you would with slip and slide. Because remember, when you slip the number to the end, you get that number, right?
Yeah.
And then you still have the negative 8 as your linear coefficient. You still have to factor that trinomial, which means you have to find those magic numbers anyway, right? So why not just do it with grouping where it's rigorous, where that is equal to that? You see, and then if we just group this thing, I mean, look, we can take out now, if I take these two terms, if I factor out a 3x,
So why did
I'm
we
left
put
with
X?
x minus 4. Well, I know I'm going to get an x minus 4. I just get 4 times x minus 4 equals 0, right? So x minus 4 times 3x plus 4 equals 0, and I got my solutions. Right?
Yeah.
Okay, but like, I'm confused. I get it, but I don't think I do it on my own. Yeah.
I mean, just try it this way a few times and you will.
Well, I don't know how to like. What do you do? Multiply.
Okay, so
N times
but
N
is it the
plus
green
N.
part?
Magic numbers.
Is the green part? Okay, the magic numbers.
What do we do?
The magic numbers have to multiply to AC, so they have to multiply to A times C, so negative 48. And they have to add to B, so they add to negative 8.
And then
right.
we put them with X's.
And then
Right, and you're
then
using
splitting
those to
the middle
split
term.
that
Because
coefficient.
12x plus 4x.
Oh,
would
oh,
give
yeah,
you
see what I'm saying?
8x.
Yeah.
Okay.
Okay.
You just
Once you
multiply
find
the
magic numbers.
Okay.
So do you see the strategy? The strategy is you can split that middle term up into 2. Now you have 4 terms instead of 3, and you can factor by grouping.
Okay.
And it's guaranteed to work. If you find magic numbers, it has to work to group it. Okay. So there are our second derivative zeros. Okay. So those are potential zeros of the second derivative are potential what?
Potential
Potential
points of
inflection.
inflection.
Inflection points. There
I
it
also
is.
said inflation.
Man, I just tossed you that softball. Oh my gosh, you were wanting to say that all period long. I just gave you your chance.
I slept.
Okay, so let's go back. I'm gonna cut and paste and let's just kind of abbreviate all this stuff and go back and make a table out of it then.
I've never seen it done that way. What the heck? Me neither. Maybe we have.
Yeah, you have.
Well, I guarantee you
We've
have.
done it.
I do not remember that.
I have never
I
done
didn't
slip
slip
and
Well, I
slide.
guess I always thought slip and slide was like easier because that's what I did once. So I just
I've
disregarded.
always done slip and slide.
I just
for life.
disregarded slip and slide.
I disregarded any other way of doing it. Like I can't complete the square. I don't know how to do that.
I will put myself through more work through the car.
Okay, well, we need to review.
Learn how to do stuff.
We need to review completing the square too, because that's a pretty good strategy sometimes.
Is it like V over 2 squared?
Something like that.
I watched a TikTok on it the other day because I wanted to figure out how to do it.
Good for you.
And no, I never actually got that far. I was trying to help you with this homework. I couldn't do it. It's like college algebra. 'Cause I tried.
Okay, there's.
I
Oops.
did my slip and slide. And it didn't work.
If the quadratic formula gets too hard, I'm done. I'm just gonna click no solutions on Excel. I hope it's right.
The quadratic formula is
Negative b.
Who made a song? Who taught us a song?
Mr. Oya
Yeah,
did.
minus-
It
You guys, do you not remember my class at all? Oh my
No,
gosh.
I do.
I
I
do.
remember learning a song. I was getting it confused because Miss Robinson taught us a slope song.
Fifth
too.
grade.
Ah, okay.
Or the song.
Yeah, did we not learn it with
With Robinson's.
Robinson?
Yes.
Oh, I gave her my song.
Yeah, we
yeah.
learned a song from Robinson. But
Yeah.
We also learned one about the quadratic.
Yeah, that's.
Did we also learn like the graph? There was that part of the song.
Let's see.
It's
The one
part of
where-
it.
the one where it's like.
Is it
Apparently
like
sophomore
this?
year, algebra 2 is a blur.
Yeah, it's
Yeah.
this guy.
I got
the
the
Yeah,
It's like this.
yeah, something like that.
This is 0 fun.
That was like a weird year, wasn't it? Was that the first?
Yeah,
year
it was.
that
It
we-
was like
Yeah.
half mask.
Yeah.
So,
Okay, so
Jay.
critical numbers. So first derivative critical numbers were plus or minus 4.
It was also seventh period. We couldn't think.
And obviously our domain's all reals, right?
yeah.
Oh, yeah.
Oh, you're saying-
I still don't know how to find the buildings sometimes.
Okay.
It's not all reals, I don't know.
Oops. And our second derivative zeros are 4 and negative 4/3.
I don't know how to find the ring.
Yeah, no clue.
Oh, you can hear the rain outside.
Dang.
Just had to
Golden
be-
silence for
Yeah,
intense practice for the era.
This one has a
I had time to joggers, our windbreakers, the quarters in, and then my shorts, and then
Go
just
on a
gonna be
train.
gloves, like I'm gonna it's like
Ready
Okay,
for
good.
all
Everybody good with that?
Yes.
That summarizes everything we did?
Yes.
Okay, so we always want to work as far down as we can. So then first or second derivative test here.
What?
First or second derivative test for this critical number.
Second.
Second, for sure,
Yeah. It's
right?
our Y.
How come?
Because
Double prime.
it's
Because we've
so
calculated, so when do you use the second derivative?
if
If,
you want
well, whenever you want, true.
What did, I'm trying to find something.
If you, in this problem, if we weren't asking about inflection points, then it would be kind of a toss-up. Not really, I still think you use it. But there's no compelling reason to calculate the second derivative other than the second derivative test. But it's so easy that you should. The second derivative, because we're dealing with a polynomial, calculating the second derivative is trivial, so do it. Because it ends up being easier to use when you're finding extrema, right? All you need is one sign down here.
Oh,
It's like
yeah.
You see my point?
Oh,
Okay,
yeah.
so the sign of the second derivative at negative 4 is what?
Yes.
It would have been easier for us to analyze this where the second derivative was factored, which was right there.
So we.
It's smiley or non-smiley.
Okay,
Okay, I'm really confused about this.
so
Well, we're doing the second derivative test. aren't we?
so there's factored form, right, of the second
Yeah,
derivative?
yes.
Okay, remember
Yep.
that. Okay, so what was it, 3x plus 4?
Yeah.
Yeah.
Okay, so then it's easy for us to evaluate this at negative 4 At -4, we're just gonna get negative times negative, right? Which is positive.
Smiley face.
Okay, so we get a smiley face.
We get one of these.
Whoops.
Yes. Beautiful. Stretch out.
Okay. So we get a minimum there. What's going on? What about here? Well, here the second derivative test has failed. Okay, but this is a place where
we go back up.
we go up and use the first derivative test. Sure. But I think it's easier. Gosh, I can't do it. I gotta teach it my way because it's so much better.
It's okay.
Teach it
Show
your
us
way.
your
Your
way.
way
Show
is
us your
better.
way.
Your way is better.
It is better, no question about it.
P test.
So
Sorry,
when we
Rachel,
pick a
I'll-
test point, I'll defend why this way is better.
Okay.
If we pick a test point here at -1, let's see, yeah, -1. I guess I didn't put that in a very good spot, did I?
No, it's okay.
And this is up here at like
Yeah, that's
5.
what I mean.
Yeah.
Okay, so let's go down and work in the second derivative row. So at -1, we're gonna get negative times positive, which is negative, right? Agreed?
Yeah.
At 5, we're gonna get positive times positive, which is positive. Okay, well now we know what it is. It's an inflection point. It's not a minimum or a maximum, it's an inflection point because it's a point of transition of the second derivative.
Uh-huh.
But look, we
Yes.
killed 2 birds with 1 stone. Not only do we know, excuse me. Not only do we know,
You need to start on that real quick.
yeah,
If only you would have finished it before Christmas break.
that's right.
You would have been all there.
You can put like a big sticky. I bought
So
this
now-
sticky.
Not only do we know that this is an inflection point, it does double duty, and we also know that this is not an extreme, right?
Yes.
If we had been working
Yeah.
in this row, we could have inferred that stuff, but it would have been tougher. We would have found,
Yeah, we want to know.
let's just show that. Not much tougher, but a little bit. If I evaluate the first derivative at -1, first of all, it's harder to do
Yes.
because it's a bigger polynomial, right?
Yeah, that's tough.
And so I could do it.
Yeah, that's
I'm
better.
gonna get, let's see,
I hate it. That's not.
it's gonna be positive and positive. Okay, but it's, that doesn't really tell us if it's an inflection. It does, but it doesn't really tell us the nature of the inflection point, does it? Right? Now we know the concavity is going from negative to positive, and that does tell me what's going on with the slope. If I've got a 0 first derivative, so I know I've got a horizontal tangent, and I'm going from negative concavity to positive concavity, well then it has to look like that, doesn't it?
Yeah.
Right? And so I know that the slope has to be negative value to the left of that 0, so I know this is a negative in here. Right? I can fill in the rest of the table pretty easily. Everybody see that?
Yeah.
I know to the right of this, it's positive value, so I can fill in that guy pretty easily without even having to evaluate the first derivative. Just by the sketch I get of that inflection point, I know those are both positive. Okay. And then what's going on here? Well, we already know because look, we found out from the second derivative test, we get positive concavity and negative concavity. And so this is also an inflection point. Is it an inflection point where we have a horizontal tangent? No, we don't have a 0 here, right? So this is going to be a slanted inflection point. Everybody get that?
Come again.
I mean, so it's gonna look like we're going from increasing. We know that let me do this. Let me put that plus sign here. Oops. Right? Because I know that the function's increasing to the left of this 0, so I know that's positive. So I know that I've got the no matter what, the tangent of the slope of any tangent line to the curve between -4 and 4 is positive, right? I know that the function is increasing on that interval because there are no critical numbers in between -4 and 4, right? So if I take that combined with the fact that we're going from positive to negative concavity, doesn't that tell me that it has to look like this? Well, other way around. It's doing that, right? Makes sense? It's going
That
from,
does not make sense.
I see what you're saying.
you see what I'm saying? It's gotta be, it's going from positive concavity to negative concavity. But the slope at that point at negative 4/3 is positive. So it's not this kind of
How
a
does that work?
inflection point.
It's because it's like
Picture
super
the-
flat. It's like a super flat region of function. Right?
Yeah, I mean, you can have inflection points like that do this, right? Like there's a picture right there. Okay, so there was our inflection point at negative 4/3 right there. It's going from, if we divide this up into concavities, see, look, over here,
Oh, right,
F double prime is positive.
right.
Here, it's,
Oh, okay, I'm with you now.
okay, see what I'm saying? From
Yeah.
there over to
Yeah.
here,
Yeah,
F double
it's
prime is
below,
negative.
He's under and then it goes like.
And there it's positive.
Oh.
right?
Sure, yeah.
And so we get a pretty accurate sketch of our graph just based on this table, because that's the only way, only way we could sketch it,
Yes.
right? There's only one extremum. That's it. Okay. Okay.
Is there any symmetry in that, or no?
There's not. There's not. We know there's not because we have both odd and even exponents in our polynomial, so it's neither. You have to have exclusively even for even symmetry or exclusively odd for odd symmetry. Both contaminates it. It's not. Okay.
That's what I'm saying.
All right. I think that's a good place to stop.
Interesting.
I think I'm done.